So, let's talk about, shut up! Let's talk about the midterm.
Oh, yeah, that's just Thursday.
It's canceled. All right, so midterm is going to be on Thursday, and I'll have grades up by that night because I have to have midterm grades turned in by, I guess, midnight on Thursday. So, grade turnaround should be pretty quick on them. It's going to be designed to take about an hour, but you have the full hour and 15 minutes to work on it. It will be a lot of programming and a lot of language theory stuff. I would say at least minimum 50% programming, maybe more. Depends on what kind of interesting questions I come up with. So let's kind of go through the current slides so I can kind of point out things that I deem to be fairly important that will likely make the exam in terms of questions. And then if there's anything you want me to go back and review in preparation for the exam, we can do that. And then we'll go back and try to finish fixing what we broke last time. Okay, so certainly you should be familiar with the stuff in our toolbox. So defines, cars and cooters. You should be very good at cars and cooters. So fair questions would be, me showing you a list, telling you to, write the appropriate car, cooter, combination, dealy, flippy to extract some element from the list. That kind of stuff. Understanding what predicates are, using a couple of the predicates we have access to, symbol, number, list. Certainly understanding what a lambda calculus expression is, both from a scheme perspective, being able to define functions, as well as our grammar that we've been working with in here for our lambda calculus expression that consists of a var expression, a lit expression, a lambda expression, and an app expression. How those guys kind of all work together to accomplish something. List ref, you can accomplish anything you can with a list ref using cars and cooters, but sometimes list refs are easier. Difference between append and cons. So make sure you're familiar with those guys. Append glues two lists together. Cons constructs a list given an element and a list. So the results are going to be different. Well, at least potentially will be different. Let's see. Certainly map. I like, there'll almost definitely be a question dealing with the map tool for mapping a function across a list. So I might ask you to write something with map. I might ask you to tell me what a particular function that I provide for you does that's done in terms of map, possibly both. I can almost guarantee map will make a appearance at least once. Let's see. All right, so we talked about predicates, cars and cooters. Clean star, I'm not going to ask you anything about that. We've pretty much already been working with it. Certainly being able to read grammars and give me an example of something from a grammar. So I might give you a grammar, then ask you to provide an example of production to from that grammar or something like that. And you should understand what all those words I just said mean. Okay. So a grammar is the whole thing. A production is an individual rule within a grammar. Okay. You should also be able to write grammars and the necessary productions, at least at a reasonable level. I'm not going to be looking for absolute perfection, but if I ask you to, here is a list of numbers, for instance. Let's say I define what list of numbers is in a paragraph, and then I ask you to define a grammar that represents list of numbers, something like that. You should be able to give me a reasonable attempt at that grammar. Whether it's 100% perfect or something is relatively unimportant. I'm looking for competence in terms of, do you roughly know what a grammar is and what its purpose is, and that jazz. Yeah, certainly our Lambda stuff is a big deal. Yeah, you should be able to ask questions. Difference between occurs free and occurs bound. You know, I like asking questions. I think we had it on a quiz one day that dealing with write me an example of a lambda calculus expression where a variable x occurs both free and bound. Think something like that. Those would be kind of fair game type questions, kind of proving that you understand the difference between occurs free and occurs bound, where variables are actually bound in the context of a lambda calculus expression, and kind of that stuff. I wouldn't have you write something like occurs free or occurs bound on the exam. So the programming questions on the exam are going to be, you know, there'll be a couple that are going to be more just kind of utilitarian, like kind of like in the early homework assignments. You know, write something that takes a list and returns a new list with all the odd number things removed or something like that. You know, little programming practice type things. And then there'll probably be something with variable environments. So I might give you an existing grammar and tell you to write something in terms of cons to kind of process that grammar. But I wouldn't ask you to write something as kind of complex as occurs free on the exam. You know, it would be a miniature version of something like that. Certainly let, understanding what a let is, why we need a let. I don't know that I would ask you a programming question that required a let. I'll say it's fair game, but typically when you need to use a let, you're dealing with a little bit more complex question. And it's not my intent to ask you super complex programming questions in a timed exam type thing. So my guess is you won't have to program anything with a let. That doesn't mean you can't, but you wouldn't have to, would be my guess. But certainly you should know what a let is and why we might need them for creating kind of local environments within our code. Oh, and of course bigots are going to be on there. Have to have bigots. Remember the bigots? Yeah, it was a pretty racist class. That's right, Doc? All right, so now, even having said that, I think your book actually wants you to pronounce it bidgets, but I'm not sure that's any better. It's less funny, certainly. But I probably would not ask you, well, for starters, I probably would not ask you anything specific about the bidget stuff. We already wrote it. And realistically, it's a little bit more complex than, again, I would want you to have on an exam. So if I had you answer something specifically related to bidgets, it probably would not be programming. It would probably be me giving you an example of something and telling you to do something with it. You know, probably that conversion stuff. I can almost guarantee there's going to be a conversion question. And we would do a hex to something else or whatever. Yeah, you guys have to be able to do that. So that's going to be worth 95% of the exam if you miss it. Okay? If you miss it, your max score is a 5.
What's the difference between a bidget and
A bidget and a midget? I think there's vast differences.
One's a small widget.
What? That might have been phrasing, I'm not sure. All right. So, yeah, so as an example, you know, this might be a fair game type question for one of the programming questions. I would say this would be an easier one, right? But this type of question would be fair game. Take a list in, write a Lambda procedure that goes through every element of the list and does something with it, sums it up or wraps it in another list, whatever it is, that kind of stuff. So I'm going to have a group of questions that are geared towards proving that you have some level of competence with the scheme stuff. So less about language theory things in general and more about just have you been doing your homework on your own or are you copying off somebody else, that kind of stuff. So I wouldn't look forward to a whole bunch of those. I'm thinking like 1 or 2 questions like that, and then a bunch of other questions that will deal with more of the theory stuff, taking a grammar, doing something with it, that kind of stuff.
So you're saying all of these are going to be like 1-star to easy 2-star problem equivalent?
They're all going to be 4 stars.
I would say easy 2-star at worst. Yeah, I mean, again, keep in mind the goal of it. Well, first of all, let me remind you of my exam policy as well. I do this every year, but just in case you forgot, if you come in and bomb this exam, you know, if you come in and do better on the final, I'll replace your midterm exam with whatever you got in the final. Not the other way around, though. Okay, so I don't think you should be completely penalized for one bad day. If anything, the midterm is mostly there for you, let you know whether you know the stuff at the level you probably should know the stuff. If you don't, that allows you to evaluate why. Is it because you're not putting enough time in? Are you relying too much on somebody else to do your homework? I want you to work with other people on your homework, but to an end of learning, not to just completing, right? So completing is not going to help you if you come out and bagel the exams. So, so then 40% of your grade you got to zip for. That's not really helping anybody. So, you know, first of all, you have that. I want you to come into the exam and try to do well, but understand that it's going to be relatively low stress because you have a backup chance if you do bomb it. On top of that, the exam in general is going to be designed to measure competence, not expertise. Okay? I'm not looking for you to write perfect procedures. I'm not going to take off points if you forgot an extra parenthesis. If you put no parentheses on the entire exam, then that's probably incompetence, but I'm not going to count parentheses and things like that. I'm looking for you to show me that you pretty much know what you're doing. Okay? You know, and that's going to earn you plenty of points. All right. Let's see.
What
I'm not kidding.
Don't mind me. I'm doing an exercise. Front row.
Could you have said that like in a less phrasing way?
Like or a creepier way.
Don't mind me. I'm good.
I'm just doing an exercise. Okay.
Just gotta work the elbow.
All right. So here again, here's the conversion stuff. I almost guarantee I will have a conversion question on there. Not even writing code to do it. Just here's a number in some base, convert it to some other base. 100% guarantee. And like I said, if you miss that, it's 95% of the exam.
I'm gonna fail.
You guys are basically, most of you are seniors or high juniors, right? You should be able to do that stuff. Okay. We talked about design patterns in here.
I don't know that we went into that much detail.
Yeah, well, I won't. It's not going to be on the exam. Doesn't matter. Yeah, I probably brought it up in for some example we were talking about it here when we were connecting something back to Java or something.
Yeah.
But I won't test you on design pattern stuff. It's important stuff, but really unrelated to what we're doing in here from a core competency perspective.
That's like this in kind of place.
Yeah, it had to be when I was making a connection back to Java for something. Let's see. Yeah, it definitely was, because this is our environment type stuff when we were talking about what's the purpose of an environment with Java and where things are stored and why and that kind of crap.
I think that's when you were talking about, too, why we're even using instructors when we probably, I mean, it could technically be easier not to use them, even though we are using them. Yeah.
Okay, so certainly the environment stuff. So if I gave you a grammar for an environment, maybe in terms of constructors, So, you know, I gave you the grammar and the equivalent constructors, or even if I gave you a grammar for something and told you to build me constructors, you should be able to do that. You know, so like we had the constructor for the empty environment, and then we had a constructor for extend environment that takes two parameters, the value you want to extend it with, and, well, name value pair you want to extend it with, and then the environment that you're extending. That type of stuff. So I should be able to either give you the constructors and tell you to construct me an environment that has some variables defined with their equivalent values, or I should be able to give you the grammar, and you should be able to then provide me with a set of constructors for supporting that grammar, not necessarily with environments specifically, but leveraging what you learned about environments, and then maybe I come up with some made-up grammar and ask you to define constructors for this guy, something like that. Let's see. The idea of apply expression. Really all the stuff we've been doing with more recently. So this would really be, so apply is more apply env, apply environment. And then we were talking about how apply expression would be kind of we call it eval expression in our current interpreter. But the idea is when we call apply env, what are we doing? We're looking up a variable name and extracting its equivalent value from an environment, right? Getting the most local value associated with a particular variable, especially when you consider our environments are collections of scopes. Evaluate, eval ex, what do we call it, expr or exp, whatever it is. Evaluate expression, whatever we name that function, is kind of like the apply env for expressions. So this is the guy that takes in an environment as well as a lambda calculus expression and evaluates it, comes out to its final answer. That's the stuff we've been working on more recently. So understand how that all works, be able to read code associated with that. It would be fair game for me to ask you to write a portion of it. But certainly, again, I wouldn't ask you to write something that complex on an exam. It would be something that takes your understanding of that and I put it into the context of something much smaller scale. You know, maybe I give you a very simple grammar of numbers or something like that, or grammar of math expressions, and tell you to write the constructors or write an interpreter for you know, processing single layer lists of math expressions, or a parser that converts from one format to another and an unparse, that kind of stuff. So taking things you've learned in here with our complex assignments, but applying it to simpler problems, but proving that you understand the concepts. Okay. That's all what we were just talking about. Okay. So at a pretty high level, that's kind of what the exam will be. So given that, what things do you want me to go over or re-go over, or examples you want me to give you to help prepare you for this exam? And then we're going to go back and keep working on what we were working on last time, which we have some sort of bug that I'm sure we've completely forgotten, so whatever. Go ahead.
What are bigots?
What are bigots?
Yeah.
So that was our representation from the book of how do we store large numbers.
Midgets or little.
Yep.
Numbers.
So here, let me open up. What's the name of the application we use to? No, to read the book.
Oh. Preview.
Preview. That's what I'm looking for.
Nailed it.
That's the word I'm looking for.
Reading the essentials of program.
All right, and then let's do.
Bigot. Find the bigot.
Yeah, so this guy right here. where so if n is 16, so we kind of make a we decide what the base is going to be for our bidgets. And in this case, we're saying the base is going to be 16, so that means that 33 is actually the bidget 1, 2 in base 16. So 33 in decimal, when converted to, oh, and it's backwards here. So 1, 2, it's in little Indian form. So this is actually 21 in hex is equal to 33.
Little Indian form?
Little Indian. E-N-D-I-A-N. Least significant digit first, I guess. So let's say the bidget 33 translates into that, which is actually, in our world, 21. So this is 1 in the ones place, this is 2 in the 16s place. 16 times 2 is 32, plus 1 is 33. So the bidget 33 is a base 16 number representing decimal 21. But we represent decimal 21 inside of a list as the list 1, 2 in bidgets. This is the little Indian thing, where the least significant, this is the ones place, comes first. As opposed to over here, the least significant comes last. All right, so this is when we had to implement the 4 different operations for bidgets in terms of those functions that were up here. So 0 is 0, successor, predecessor, or how do we add 1 to a bidget, how do we subtract 1 from a bidget, so on and so forth. So that's what our bidgets were. Remember now? All right, what else?
Well, I'm kind of wondering about like reading grammars and credentials.
Okay.
Just like a kind of like a basic simple like how to read it, I guess.
Okay. Let's just see if we can find a random, well here, let's go to a kind of a smallish type grammar that we have in here somewhere. Go to like a list of numbers or list of symbols or something like that, one of our earlier grammars. All right, so this is, I guess, a fair enough example. So here is the grammar for an S list. And an S list is a list of 0 or more S expressions. So this is that clean E star thing that they happen to write it in there. So an S list is a list. That's where the open and closing parentheses come in. And it contains, an asterisk means 0 or more, S expressions. What's an S expression? It's one of these guys. An S expression is either a symbol or it's an S list. All right, so really this is, an S list is 0 or more symbols or S lists. That's what's in here. So being able to read through that and then create me examples of that. So for instance, if I asked you to give me an example of an S list given this grammar, what could you say? So it's anything that meets the, there's only one production in each of these grammars. So technically this is a grammar and this is another grammar. It just happens to be that this grammar is defined in terms of this one. So what would an example of an S list be?
Plus sign. A list containing
So S list, you said just a plus sign? Okay, so let's go back here. an S list must be a list. Open and close parentheses right here.
I mean, in a list.
Okay, so a plus sign inside of a list. Is that a S list? Is this a list containing 0 or more symbols or S lists? Yeah, that's an S list. What else? Go ahead. A list containing a list containing a plus sign like that. Is that an S list? Here's a list. Oh, this guy right here. Okay, so this is a list containing 0 or more S expressions, where an S expression is either a symbol or it's an S list. Well, this guy's an S list, which is a list containing 0 or more S expressions. That one happens to be a symbol. So here's a symbol inside of a list, inside of a list. That's an S list. Would this also be an S list? Does that fit the requirements of an S list?
Yeah.
This guy's an S list right here, right? So it's a list containing 0 or more symbols. This guy's an S list right here. That's a list containing 0 or more symbols. This whole thing's an S list because it's a list containing 0 or more S expressions, right? So these are both S lists. Okay? It wouldn't be a symbol unless it was quoted like a 1. So it would be the symbol 1 instead of the number 1. Right, that makes sense with the kind of reading grammars. Now, having said that, what if I wanted you to, so kind of some examples if I base questions off of this one. So I might ask you to give me some examples of an S list like we just did. Maybe I ask you to write a predicate for S list to determine whether a given input is a S list. That would be a fair game type thing. What does it mean for something to be an S list? Well, for starters, it has to be a list, right? Okay, and then if it is a list, it has to contain 0 or more things, right? All right, so if you were to write the code for a predicate S list question mark, how would you write this?
Is there a list predicate?
Say this again.
Is there a list predicate?
There is. So let's kind of come in here. So define S list question mark to be a lambda that takes in a single list, and this guy's going to return true if that list is a S list and false otherwise. So in order for something to be an S list, it definitely has to be a list. Correct? All right. So if it's not a list, then what can we say? Return false. Okay, so if, actually let's just do this in a cond. We'll do something. Else false. That. All right. So if we're not even looking at a list, we can return false. If we are looking at a list, though, we need to do something else.
Determine if it contains.
Okay, so right off the bat, in order for something to be an S list, it must be a list. So if we're inside this part right here, we know we're dealing with a list. So we've already met the requirements of this part, the opening and closing parentheses. It is a list. Now we need to look at the contents of that list. Right?
You say can contain 0 or more, or 1 or more?
0 or more, because it has the asterisk.
Oh, okay.
This says 0 or more.
I couldn't see that first.
Okay? So if I have a list, in order for it to be a S list, the contents of this guy must be S expressions. Right?
Anything but a number.
So what's an S expression? Okay, it's an S list or it's a symbol. All right, well, all S lists are lists. Not all S expressions are lists. Some of them are also just symbols. So maybe we write a thing for S expression. Actually, let me just do this in a separate box here. Sex. Still sitting a little funny. Well, at least better. All right. So this guy is going to be a lambda that's going to take in an exp, let's say. If it's a list, do one thing. If it's a symbol, I got to change this to exp here. So if I'm looking at a symbol, I'm going to return true, right? All symbols are S expressions. Now, if we're looking at a list, we only want to return true if what is true?
The list contains
in order for an S expression to be true, in order for it to be an S expression, it either has to be a symbol, which we handle right here, or it has to be an S list, right? Do we already have a predicate for handling S lists? All right, so we'll just return S list of our expression. Else false. So that is our production for whether or not something is an S expression, or our function for our predicate for whether something is an S expression. If it's a list, return true if it's an S list. If it's a symbol, return true. Otherwise, if it's neither one of those guys, return false. So now we're back up here to S list. So an S list, if it's a list, what are we going to do? We need to find out if it's a list containing only S expressions. Right? How do we do that? You want to map something. What do you want to map? So map S expression across the list. Map this function across every element in this list. So map. What will this boil down to? What kind of animal will that boil down to? A list. 100% guaranteed map always returns a list, correct? What types of things are going to be in that list? What are my options for what that list might look like given this, this current scenario?
Be a list of trues or falses.
Or the empty list, right? So it'll be a list of Booleans, trues and falses, or a nothing list. All right. So in order for something to be an S list, then what is the when we have that list of trues and falses that come back? How do we know that something is not an S list? If I find at least one what? One false in there. All right. So if there's one false inside of this guy right here, one false, it's not an S list. Otherwise it is. Right? So we can write a function that goes through and counts the number of falses, and if it's 0, then it's a S list. If it's not, then it's not an S list. What else could we do? Any fancy schmancy things we can do to this guy? Didn't we figure out that you can actually apply and to a list of things? Or maybe there's a version of and that allowed you to do that. We can and across the whole thing. But in our case here, maybe we just do a define check to be a lambda that takes in a list. Something like that. We'll just and everything together. And the car of the list onto whatever check returns for the cooter of the list. So we'll get and true, and true, and true, and false, and true, stuff like that. And if there's even one false in there, the whole thing will fail. All right, so this would be a predicate. If I asked to write a predicate for S-list, it would be probably requiring all three of these. If I said just write a predicate for S expression, assuming there's already a predicate for S-list, you would only have to write this guy, something like that. Okay, but these would be kind of the simple functions that you should be able to write.
Going on to the same thing, what kind of constructor did you ask us to write?
Well, like the constructor stuff for a, I mean, it would kind of be based off of like an environment. So maybe I say we have a language of fractions, let's say. So you might have to write a constructor for a to construct a fraction, let's say. So a simple guy here. Let's steal one of these things here. Something like that would be a constructor for a fraction. Taking a numerator and denominator, build a list out of those two. Now we have a fraction where it's a two lists. First element's the numerator, second element's the denominator. We might have a add fraction constructor where it takes two fractions as parameters and produces a new fraction. That is the sum of those two fractions, something like that. Okay, so in general, constructors are fairly easy. They're just wrappers to put things into certain formats, because ultimately, at the end of the day, if I want to represent the fraction 1/2, I would say fraction 1/2, like that. And that guy would ultimately produce for me the list 1/2, but I don't need to worry about how a fraction is actually being represented. I just know I build a fraction this way. All right, then if I write another constructor for define add fractions, and this guy takes in a lambda f1, f2. So now this guy's going to take in two things that look like this. You're going to have to look at the denominators to figure out what the common denominator is and kind of do the math from there. So this would be a constructor for adding two fractions, producing a new fraction. So we'd still call it a constructor because it does ultimately produce a fraction. Make sense? What else?
Did you say knowing the code that we've written in class is useful? Like studying that and all?
Well, certainly useful from the perspective you should be able to read it. Like I said, I'm not going to ask things as complex on the exam as to what we do in class. It'll be smaller scale stuff like we just wrote, things that aren't dealing with, really heavy, how many cars and cooters deep do I have to go until I until I extract the right piece. But certainly being able to read the code from class would be beneficial. I doubt I'd have anything on the exam that is as complex, even reading-wise, as what we're dealing with right now. Because, right now it's getting so big that we're having to draw pictures outside of it and things like that. So that wouldn't be appropriate for the exam. But certainly being capable of reading it would be important. Go ahead.
Will any bribes be taken?
Sure, but it's be expensive. A high-level course, probably a tough exam, so expensive bribes, I would assume.
New boat board?
Well, I could do it. Huh? It's at the shop now, having them look at the motor since Nick broke it.
That's my fault. You had it running after me. Sorry.
Emphasis on sorta.
How many pounds of bacon?
I have plenty of bacon. I don't eat bacon. Yeah,
I was
How many?
You should have.
I was really.
Why didn't you?
Because we were busy making the fridge messy.
It's true. All right, what else about the exam?
How many tears collected from baby goats?
From baby goats. I still haven't gotten my.
I
haven't gotten my bottle of tears from Levi yet.
Oh, he said bucket. Was it just a bottle or a bucket?
I don't remember now. I think he maybe just said I've been collecting tears for you.
Now, if he cries upside down, we'll just roll back.
All right. What else do you want me to go over about this exam?
If you cry during the exam, you get an A.
No.
What if I slip you?
Just some of your pain pills? You turn in your exam with a little baggie of Vicodin on.
Why would you need that? You just have pot over the weekend.
Should we go over a curse free and curse bound real quick?
Okay, the functions themselves, or just what it means to be a curse?
Just like an example real quick.
Okay.
Just like I think you did a quiz or something, just like that same quiz.
Okay, so for example, let's do occurs free versus bound. So first of all, we have to think about our lambda calculus grammar, which shows, first of all, we need to find out where things are bound. Okay, things are only bound in the lambda production of our lambda calculus procedure. So let's get to wherever that guy is defined here. It's going to be right before this. Maybe they introduce it right after occurs free. Oh yeah, it is right here. Okay, so here's kind of our simple grammar for our lambda calculus expressions. So this is the one that still only allows one identifier. Okay, punchline here is out of these three productions, the only place where a variable can ever be bound is right here. Okay, so it can only ever be bound right here. It can also only ever occur right here. Okay, but this guy's a lambda calculus expression, so it could be any one of these. All right, so things are bound right here, and then they occur right here. But now let's look at this from this perspective. So I'm going to go ahead and say we're going to say lambda x. In this particular case, x occurs bound. It's bound in this parameter list right here, and then it also occurs. So in order for something to occur bound, both things have to be true. The variable must be bound. The variable must also occur. Okay, if it's just bound but never occurs, so for instance in this case, x does not occur bound. X is bound, but it never occurs. Therefore, it does not occur bound. Similarly, y occurs free. It occurs, but it's never bound. All right, let's take this a step further. So let's do lambda x y. Okay, Does X occur bound here? Or free? Or other? X is bound. It's actually bound 2 different times. But X never actually occurs. Okay, because X can only occur in this part of the lambda calculus expression. So in our example right here, X is bound twice. Here's a global definition of X, and here's a more local definition of X. So we actually have X added to our environment twice in terms of binding. All right, but the only place anything ever occurs is right here, Y. And Y occurs free in this case. It's never bound anywhere, and X never actually occurs. All right, so don't get confused with where things are bound versus where things can occur, because it's easy to get tricked into thinking that, oh, X occurs right here, therefore it must occur bound. It's not the case. This is a function. This is its parameter list. Here's another function. Here's its parameter lists. Parameter lists do the binding. It's not where things can occur.
Would you ask a question like, does X occur free or bound, or would you ask a question more like, write a lambda calculus function that X occurs free?
Either. Yeah.
You would ask us to write one.
I very likely will ask both of those questions. You know, tell me, does X occur, free or bound? Or maybe I might give you the option and tell me how X occurs in this expression or something like that. I might also ask you to write the expression like, give me an example where a variable X occurs both free and bound. That's a good one. So based on this, if I wanted you to write a procedure where X occurs free and bound, what would you write? Again, here's our grammar. So if I gave you this grammar for a lambda calculus expression, and I told you, write me a lambda calculus expression where X occurs both free and bound, what would you write?
Lambda parentheses y, then x parentheses.
What do you want me to say here?
Y inside the parentheses, and then an x, then a parenthesis, then another lambda.
Like this?
Yep. X inside, and then y. Oh, and then x, yeah. And then
Okay, and what do I do? I mean, these are just 2 separate guys. Do I need to put these in a list?
yes. That'll do.
So this is our app expression, right?
Mhm.
That's a list containing 2 lambda calculus expressions. The first expression here, X occurs free. It occurs, but it's not bound. And the entire environment governing that is that guy right there. This side, X is bound, X also occurs, so it occurs bound here, and it occurs free here. Could have also written this just by saying X over there. This is X occurs free. It's there, it occurred. It's not bound by anything because there isn't even a binding production over there. And then X occurs bound right here. So that would be a fair type question. Give me an example where something occurs both free and bound, or things along those lines. Yep.
Can we go back to the preview? Isn't that first production then it can occur there?
Well, it can, but it's because it occurred here. It's a lambda calculus expression. So I get what you're saying. When I pointed out that things can only occur right here, it's anything that's a lambda calculus expression. So since this guy is a lambda calculus expression, it can occur there. It's just an identifier. Maybe the better way of saying it is the only possible chance of something occurring bound would be if it's literally inside of a lambda, like this. It's only possible for there to be a binding in that second production there. Other than that, things can occur free if all we have is that production. So like if I just put the symbol Y out of the blue, if this was my entire lambda calculus expression, just that, and I ask you to tell me about that, you would say that Y occurs free. It occurs, it's not bound, therefore it occurs free. All right, what else? That's it? So we're all going to ace this?
No.
You don't think you're going to ace this? Shouldn't it be an easy exam? How many of you are worried about this exam? Anybody terrified about this exam?
How was your cat
Does that
doing?
get us bonus points? Terrified about it.
You show up, you just like really look real pale.
All I'm saying is
Write our
you're,
name on it and hand it in. Do we get 30%? That was the deal. I remember. You show up, you get 30%.
all I'm saying is how your cat's doing.
They're doing pretty well right now.
It can change quickly.
Some people soak their pants.
What's this?
The signing of the blood rule.
Oh yeah, yeah. The signing of blood rule was a mainstay until Yenter. See here today? Is Yenter's in this one? Where is he? Oh, hey, sweetie. You've lost some weight. You have, haven't you? Yeah, because you used to be a lot thicker than this.
That's what she said.
Hey. Yeah, so yeah, the signing and blood rule is now off after Yenter. I had to set Yenter's final exams last semester out to dry.
Can I sign something else?
No.
I don't know if anything can compare though when Heinz turned it in and just said thanks Satan.
That's true. That's true. All right. What's this?
Heinz is coming back? Supposedly he's coming back next semester, possibly for 2 more semesters.
I don't know.
Is he still in this major? I think he's switching to IT.
Switching back to what?
To IT, I think.
Okay.
But he's coming back here, I guess.
Should be interesting. Okay. So, anything else about the exam?
How many questions?
10-ish, 8-ish, 12-ish. Just depend. Huh?
Every single time.
Every single time.
Yeah, I typically try to make it 10, but it'll really just depend on how many questions I come up with. I mean, it could be 2.
Can I help you write it?
Yeah, it could be just 2 questions. Or just 1 question.
It's just one question. It's a conversion question.
That would be so bad if I actually asked 1 conversion question and that was it. That was the entire exam, and then people would miss it in here. As much as I've harped, you need to know how to do this, 20% of the class would miss it. It's just an embarrassment.
Well, that's why
Huh?
What if you actually did that?
There's a risk. These are all fair game questions. There's no guarantee I'm going to ask everything I talked about today. All right, so let's look back at what we broke last time.
My spirits?
Somewhere in there we got lost, didn't we? It was pretty bad.
The red text kept growing.
Yeah, we're definitely at the point now where we have to draw a picture because if I remember correctly, and if we didn't save this. All right, I think we're good. Yeah, this is what we were working on. We had a bunch of stuff commented out. This is certainly the right world. Okay, so we were in a val expression. And we were trying to handle, what we had just done is we had just added the ability for our environments to hold functions, right? To associate a lambda with our version of a lambda with a variable name. So the hope would be, let's get back to this. Let me comment out that. Go in here. Oh, actually, I think we do. We want this one up here. So we're creating an expression, and this expression is an app expression, right? This guy's an app expression. And this guy's going to take in 2 parameters, and then the body will be another app expression. This guy is a var expression. This guy is a var expression. Now, this var expression should boil down to this lambda. And then we need to apply that to this var expression, which should boil down to 5. Now, so we're going to run this guy through our, let's take it through the parser here first and just make sure that it gives us what we think it should give us. So this should be a app expression containing a lambda expression containing 2 parameters, containing an app expression with 2 var expressions in it. And then the second part of our app expression should have a lambda expression with a var expression and a lit expression. All right, so here's our app expression. The first guy is going to be a lambda expression, taking in an A and B, whose body is an app expression with 2 var expressions. Okay, so the idea is that we would apply A to B. So it looks like that guy's correct. And then the operands of our original app expression is a lambda expression x, var expression x. So this guy, that's going to be what that's what goes in for A. And then this guy is what will go in for B. So far it looks like we're parsing it correctly, correct? Can we at least agree on that? Does it look like it's parsed correctly? Okay. So now we're going to go ahead and run that program. First time through, let's see, what were we doing up here? So we know we're dealing with an app expression first. So it's not going to be a lit, it's not going to be a var, it's not going to be a lambda, so we're in this else, so it must be a app expression. So now we're trying to ask, is the first part of this app expression a lambda expression? That is this element right here a lambda? Okay, in our case it is. So what are we doing? We are mapping, I think this was our sample thing we were putting in there. So we're mapping this function. A function takes one parameter and just spits it out across the CDDR of LCE. So that would be the cooter of the cooter. Is that this guy?
Well, if it was a lambda, wouldn't it be at that lambda spot? So it'd be the cooter of the cooter, which would be the app expression, right?
I want to copy this and diagram it a little bit. All right. So let's start off by giving ourselves a text box to hold this. And then we're going to draw some pictures. I think that's where we went south last time. All right, so that's what this guy currently looks like. And let's shrink this down a little bit so I have some room. And then let's draw some pictures. So we're going to have at the very top an app expression. Okay, inside this app expression, we are going to have, so the first element a lambda, so that is to this guy right here, and the second element is going to be another lambda, and the third element is going to be a lit, right?
Shouldn't there only be 2 elements? There should be the lambda and then another lambda, right? Or no?
No, because it should be the operands for the operator. So this is actually going to be a 3 list for this particular guy. So here's our operator. This is our first operand, and then our second operand is going to be a lit expression. Does that make sense? So here's our app expression, and let's go ahead and color code this a little bit. So that's our operator. Why does it undo any text things? Just crappy Apple programming. And these are our operands. Okay, so that's the top level. Now inside of this lambda expression, we have its body is an app expression. So this guy is going to have a parameter list of A and B. So parameter list of A and B. And then it's going to have a body, and the body of this guy is another app expression. Let's change the color of this. So this is parameter lists are in red. Okay, and then let's just shift this stuff down. That down. So we're building a syntax tree for this guy. All right, so our top level app expression. Whatever, doesn't matter. Okay, top level app expression. This part's going to bug you? Okay, so our top level app expression has an operator that is a lambda expression, and has operands, including a lambda expression and a lit expression. The operator takes in two parameters, A and B, and its body is an app expression. And that app expression is going to be what? A, B, two var expressions. So we'll go ahead and steal this. That's a var expression. That's another var expression. And the first one is just A, and the second one is just B. All right, so this is the whole left-hand side. So the idea here is we would be applying A to B. The right-hand side, our lambda expression here, takes in a single x and then has a var expression x. So parameter list here is just an x. And then the body is a var expression. And that particular var expression is just an x, right? Like that. And then our lit expression is just a 5. There's our lit expression. Okay, so this is kind of the picture of what we have here. So our operator, and we can even kind of label this. This is operator. And these are rands. Okay, so this is what this guy currently looks like. Top level app expression. First element of this guy is right there. Second element is right here. Third element is right here. All right, so that's our 1, 2, 3 at that level. The first guy is a lambda containing two parameters, A and B, whose body is an app expression. That takes us to this part right here. That app expression has a body, well, has a left operator of A and a right operator, or an operand, of B. Then our second step here is a lambda expression that takes in a single parameter x and has a var expression x. And the third guy here is a lit expression that has a single value 5. Make sense? So this is a picture of our current parsed dealie. All right, so now let's go back now that we have this picture drawn out, which is I think the step we didn't do last time, which we should have. We want to ultimately write the code in here for solving this problem. So what were we trying to do here? We were trying to map something. Okay, so the CDDR of LCE. So that's the cdr of the cdr. So the first cdr is this. The second cdr is this guy.
Wouldn't you be in lambda already? In the lambda expression? Since you're in the lambda part.
Well, you're asking the question. This guy right here says, is the operator a lambda? That's what that says. Okay? It says, does bucket 0 of bucket 1 equal, all right, bucket, no, position 1. So we're burning past the very first position of bucket 0 here, which is app expression, and we're getting to position 1 here. Okay, so that's position 1. And then we're looking at position 0 of position 1, which gives us a lambda expression. So we're essentially asking, is the operator of this app expression, is he a lambda? That's what this question asks right here. Is the operator a lambda? In this case, it is. So what do we do when we have a lambda? Well, we need to, in fact, actually, let's just, I don't remember what we were even trying to accomplish with that map. I think we were just trying to see what the thing looked like. So let's just get back to this, the actual code. So if it's a lambda, what are we going to do? We're going to evaluate an expression. What expression? Bucket 1, 2. And that guy is what? So here is bucket 1, is this guy right here. This is bucket 0 of that. This is bucket 1 of that. This is bucket 2. Okay? So bucket 2 of that is our app expression. That's the body of that lambda. Okay? So we are going to evaluate the body of the lambda right there in the environment that we've extended with the parameter list of that app expression. So that guy right there is that guy. Okay, so the list AB, so that's the parameter list. And then we're mapping this function. So this has got to be where we start messing up. So we're extending env for lambda, and if you remember correctly, extend env for lambda takes in a list of variable names and then a list of values. Correct? Okay, so this guy should produce that list of values. So what we're doing is we're mapping this function, lambda x, across, and this function is going to ask a couple questions. It's going to say if the car of the guy I'm currently looking at is a lambda exp. So we're mapping this over the, what are we mapping it over? Okay, so we're mapping it across the values associated with it. So we need to map it over this. So we're mapping that function over this guy right here, these two guys. Okay, so we want to make sure we're getting at these. So we want the list containing these two guys, which would be the cdr of the original. Coder of the original should be a list containing a lambda and containing a lit expression. Let me just see if that's the case here. We do this. Let's just take the coder of this guy. We should have a list containing the lambda and the lit. Here's the first guy. Oh, no, that's where the coder comes from, because we needed to get past the app expression. There we go. It's the list whose first element is our lambda and whose second element is our list. So that's the coder. And so that gets us to the values that we need to map across. Okay? So come across here. So that's our map this guy across the coder. Okay, so coder I think is the correct thing. That gives us this guy right here. And what are we doing? We are mapping the function lambda x if the car of that guy is lambda exp. So for instance, in this case, when we get to the very first element here, the car of that element is lambda exp, correct? Since it's lambda exp, what do? We just boil down to that guy itself. That is, do not try to resolve it because it's not a resolvable value.
The
Right.
car of item 0 of that list?
Say this again?
So you're looking at the car of that entire list at the bottom there, right?
Yeah, because I'm mapping across that. So I'm going to pass this function, this lambda x function,
Yes.
this guy, I'm going to pass it, I'm going to call it twice. The first time on this element, the second time on this element.
Okay.
So the first time when I'm calling it on this element, I'm going to look at the car of that element. That's this car x thing. And check, is that equal to lambda expression? In this case, yes it is. What do I do with it if it's equal to lambda expression? Just return it as is. Basically, don't do anything. Okay? Because we're not unparsing it. We're going to parse it. We're not unparsing it. So we'll deal with that later when we actually go to pull it out and need to apply it to something. All right. So when we get this part, it should just boil down to, and let's go ahead and just build this. Well, I guess it should just boil down to that value. Nothing will change there. Secondarily, when I map lambda exp, or I'm sorry, when I map it across the same function across the car where it's not a lambda exp, which will be this guy, the car of this guy is lit exp, what am I going to do? I'm going to evaluate the expression in the current environment. Okay, when I evaluate that expression in the current environment, let's just make sure this is cut off at the right place. All right, I'm mapping that function across this list. Oh, I was missing a parenthesis there. And I'm evaluating that guy. Well, I'm extending that environment, that ENV. I'm going to evaluate that expression there. All right, so I had one parenthesis in the wrong place. That could have been our issue all along, actually. So what I want to do here is I want to take let's say
that the coder or the coder of the coder, that should be part of the extending V, right? Or no?
Huh?
The coder of the coder of LCE up top, or you're right there. That should be part of the map function.
Here, I'm just backing this off here. I know we're out of time, so you guys can pack up. I just want to make sure this is documented for next time, because I think we're pretty close to the issue.
Still so far away.
Okay, so that seemed to map the correct way, right? First guy it left alone. Second guy it actually evaluated. 205. So that seems to give us what we're looking for. So now let me just write a little comment here. Pass the
Oh, you're not curious right now to just do it?
No. Not that curious. I just wanted to make sure we had a good place to pick up next time.